34th lecture and we are going to continue our discussions on properties of scattering matrix and, if time permits, insertion loss synthesis. Last time the point where we stopped was the following. We had considered a two-port N, a passive one, not necessarily reciprocal, a passive one with the incident parameters A1 and A2 at the two ports and the reflected parameters B1 and B2 at the two ports. Then we showed that the power that is absorbed by the network is half A star transpose, if you recall, A star transpose, then identity matrix minus S star transpose times S. Is that okay? These are all matrices multiplied by, post multiplied by the matrix A, where we utilized the relationship that the power capital P is the sum of two powers P1 and P2. P1 is half mod A squared minus mod B squared A1 B1, and P2 similarly is half. The factor half comes because A is considered as a peak vector, and P2 is half A2 squared minus B2 squared, and magnitude A1 is A1, magnitude A1 squared is A1 star. We also utilized something else in this, B equal to SA, that the reflected parameter matrix is equal to the scattering parameter matrix multiplied by A. So this was the final result. And if the network is passive, let us write the final result in a slightly different form. Let us bring this 2 here, 2p, and if the network is passive, well, this is obviously a scalar quantity. The power is a scalar quantity, it is not a vector, it is not a matrix. The power must be greater than equal to 0 if the network capital N is passive. And therefore, the result is that for a passive network, the scattering parameters shall obey this particular relation, that is capital I minus S star transpose S A greater than equal to 0. And the necessary and sufficient condition for this to be true, or incidentally we also introduced the term quadratic form. Quadratic form. Any form like X star transpose B X, this form is called a quadratic form because, where X is of course a vector, X is a vector, because all terms in this shall contain product of two components of X. Two components. These two components may be the same. For example, this will contain x1 squared, it will contain x2 squared, x1 x2, and if there are other components x2 x3 and so on and so forth. Okay. So this is a quadratic form. If this quadratic form is to be greater than equal to 0, then the necessary and sufficient condition is that for the coefficient matrix, this is the coefficient matrix I minus S star transpose S, and these are the variable matrices A and A, these are the variables. The coefficient matrix must have a determinant which is non-negative. Okay, this is the condition. Now, for the special case that the network is passive and lossless, well, I argued that the determinant must be equal to 0, and in addition each term in the matrix shall be equal to 0. That is not obvious from determinant consideration, but if we take this relation that for a passive network the passive and lossless network, the relation that shall be valid is A star transpose I minus S star transpose S A should be equal to 0 if we take this relation, and this should be true for all possible vectors A, all possible variable vectors A. The only condition under which this can be true is that this matrix itself should be the null matrix. Okay, does it stand to reason? A is a variable vector, is a vector of variables, and therefore for all possible values of the vector A, the quadratic form should be equal to 0, and the only way that it can be done is that the coefficient matrix itself should be a null matrix. The proof is simple, and I would very much encourage you to try to prove it, taking A as a 2 by 1. No, it's a, yeah, that's right, 2 rows and 1 column. That is taking A as equal to A1, A2, and take B as B1, 1, B1, 2, B2, 1, B2, 2. All right. Prove that if A star transpose B A is equal to 0, then this implies that B itself is a null matrix. Okay, prove. This proof is very instructive, and I strongly encourage you that you try to do this. Now, in our case, therefore, the result that we shall have is that I minus S star transpose S star should be equal to 0. That is, S star transpose S, there is a small hitch in the proof which has to strike you. There is a small point which has to strike you in the proof, and it depends on the value of B, that B is of this form. Okay, but it's in general also true. All right. Therefore, S star transpose S is equal to the identity matrix. That is, now before we go to the next step, matrices which obey this property, that its conjugate transpose pre-multiplying the matrix gives you an identity matrix, not Hermitian. Hermitian is a slightly more special case. This is called a unitary matrix. Unitary. Therefore, S is a unitary matrix. The scattering matrix is therefore a unitary matrix. If we write this in an expanded form, then I get S11 star. What will be the next term? S star transpose. So it would be S21 star, then S12 star, and S22 star. This would be equal to, no, this multiplied by S11, S12, S21, S22. This should be equal to the identity matrix, that is 1, 1, 0, 0. If I multiply out, if I write down, there will be 4 equations now. You see, what we shall get is S11 star, S11 plus S21 star, S21 should be equal to unity. All right. Then S11 star, S12 plus S21 star, S22, this should be equal to 0. The third equation would be multiply this by this. So, S12 star, S11 plus S22 star, S21 should be equal to, pardon me, 0. And finally, the equation would be S12 star, S12 plus S22 star, S22 should be equal to 1. And if you see carefully, you notice that these two equations are complements of each other, are conjugates of each other. That is, if you take the conjugate of this, S11 star comes as S11, S12 star comes as S12 star. Similarly, this term is the conjugate of this, and the conjugate of 0 is 0. Therefore, although there are two equations, they do not express anything new, they are the same equation. So, in actuality we have three equations. Alright, is that clear? We have three equations, and if you look at the first and the fourth that we have written here, you notice that the left hand sides are real quantities, isn't that right? Left hand sides are real quantities. S11 star multiplied by S1 is simply magnitude of S11 whole squared. Okay. However, we cannot say this about the left hand sides of these curly bracketed equations. We can't say that they are purely real. Alright. They will have real part as well as imaginary part. The real part shall be 0, the imaginary part shall also be 0. But the fact of the matter is that these two equations are not different, they are the same equations. The first and the last equation, that gives us S11 squared plus S21 squared is equal to 1, and the other one is S22 squared plus S12 squared is equal to 1, alright, which shows two very important characteristics of the scattering parameters, namely that since magnitude squared cannot be negative and the sum of two magnitudes squared makes a 1, each of them therefore must be less than unity. That is, S11, S22, S12 and S21, each of them should be less than or equal to unity. One could have one of them equal to 1, then the other one shall be 0. Okay, we'll come to this. This is a very interesting phenomena. Physically, it's very simple. It's very simple to see. But notice another thing, that if the network is passive, lossless, which we have assumed, and in addition, if the network is reciprocal, okay, if it is reciprocal, then S12 and S21 should be equal, and if S12 and S21 are equal, then obviously S11 magnitude is simply equal to S22 magnitude. Isn't that right? That is, the reflection coefficient magnitude at the port number 1 and at port number 2 should be equal. Agree? These are the various interesting properties of the scattering matrix parameters. In addition, we have already stated that if one of them is 0, suppose S21 is equal to 0 at some frequency, let us say at S equal to j omega naught, let us say. What does this indicate? It indicates that the forward transmission scattering parameter is 0. What does that mean? You also recall that S21 is directly proportional to the voltage transfer function. Isn't that right? S21 is twice V2 by Vg1 square root of R1 by R2. This is S21. If this is 0, what does it indicate? It indicates null transmission. That is, the output voltage at this particular frequency shall be a 0. Okay? Output voltage is 0. Therefore, there is no power that goes out of the network. And it stands to physical reasoning that if no power goes out of the network, all the power must therefore come back to the source. Why? Because the network itself is lossless, it does not absorb any power, and therefore it follows that magnitude S11 should be equal to 1. That is, all the power that is fed from port number 1 comes back to port number 2. Now, such a frequency at which S21 is equal to 0 is called a 0 of transmission. This is called a frequency of zero transmission, or simply called a zero of transmission. So, at a zero of transmission, the magnitude S11 is equal to 1. All right, any question? Now, let us establish a relationship. The next one is a theorem which says that for a 2-port S21 j omega magnitude squared is equal to the power that is absorbed by the load divided by the power that is available at port 1. Okay, which let me clarify what this means. We have a network N which is driven from a source Vg1 and a resistance R1, and you know that in a 2-port we take the reference resistances as equal to the terminating resistances, and this is R2. P2 is the power. If this voltage is V2, then P2 is the power that is actually absorbed by the load. All right. So, P2 is equal to V2 magnitude squared by 2R2. The factor 2 comes because V2 is taken as the peak value. Okay. V2 by square root of 2 is the RMS value, square of that divided by R2. So, this is the power P2, and PA1 is the power that is available at port number 1. That is the maximum power that can be drawn from the source Vg1 R1, and this shall be equal to, this shall happen when the input impedance is equal to R1. Okay. And therefore, PA1 would be Vg1 squared divided by 2 first, okay, divided by 4 times R1. Is this clear why it happens? Okay. We can find out the current, then current squared multiplied by the resistance. Okay. That is correct. Maximum power, and it is called the available power. Maximum word is sometimes dropped. So, PA1 is equal to Vg1 squared divided by 8 R1. All right. Now, to prove the theorem, all that we have to recall is that S21 is equal to twice V2 by Vg1 multiplied by square root of R1 divided by R2. Okay. We had established this relation. Therefore, S21 j omega magnitude squared is equal to 4 R1 by R2 and V2 divided by Vg1 at j omega magnitude squared. All right. This I can write as V2 squared divided by twice R2 divided by Vg1 squared divided by 8 R1. Is that okay? 8 R1 divided by 2 R2 becomes 4 R1 by R2 and V2 by Vg1, and therefore we have proved that the forward transmission scattering parameter, which is S21 magnitude squared, is simply a power ratio P2 by PA1. All right. Next we consider two other quantities. One is called the insertion voltage ratio, IVR. They are very simple quantities, and the insertion power ratio, IPR. Let me give the definitions first. Okay, I have a situation. This usual situation that we are considering is that the network N driven by a source Vg1, internal resistance R1 and terminated in R2. The voltage here is V2 and the power that is absorbed by the load is P2, which is equal to V2 squared divided by twice R2. This is the situation. Now one argues, suppose the network was not there, suppose the load is connected directly to the source, then what difference does it make? This is what is answered, this is what is measured by the two quantities insertion voltage ratio and insertion power ratio. That is, what one does is, suppose Vg1 R1, that is the source, instead of the network, instead of inserting a network between the source and the load, suppose we connect it directly R2. Let the voltage across R2 be V20, V20 means without the network, and let the power absorbed by the network by the load be equal to P20. Alright. Then what is V20? Obviously Vg1 divided by R1 plus R2. Is that okay? Into R2. Okay. This is V20. And what is P20? P20 would be V20 squared divided by 2R2. Okay. Which means that Vg1 squared R2 divided by twice R1 plus R2. Have I done it correctly? R1 plus R2 whole square? Okay. R2 cancels, one R2 cancels. Is that okay? We shall require this expression, so be careful whether this is correct or not. R2 which was, yeah, this is correct. Okay. So let me write this again. If the network is not inserted, then V20 is Vg1 R2 divided by R1 plus R2, and P20, the power absorbed by the load, is Vg1 squared R2 divided by twice R1 plus R2 whole squared. On the other hand, if the network is inserted, then we get the voltage V2 across the load, and the power is P2, which is V2 squared divided by twice R2. Alright. The insertion voltage ratio IVR is then defined as the voltage V20 divided by V2. That is the ratio of the voltage across the load without and with the network. This is called the insertion voltage ratio, and obviously this is equal to Vg1 divided by V2 multiplied by R2 divided by R1 plus R2. Okay. This is the insertion voltage ratio. Keep this in a prominent place because we shall require this expression while working out some problems. And IPR, insertion power ratio, is given by P20 divided by P2. That is equal to how much shall it be? R1 R2 divided by R1 plus R2 whole square. Let's see, Vg1 by V2 whole squared. This would be R2 square by R1 plus R2 whole square. Is that okay? Let me write it again. IPR is equal to R2 squared divided by R1 plus R2 whole squared times Vg1 by V2 whole squared. Is that okay? Now you also notice, you also recall that S21 is given by twice V2 by Vg1 square root R1 by R2. So what is S21 squared? That is equal to 4 R1 by R2 V2 by Vg1 whole squared. Agreed? and you see that these two are very intimately related to each other. The insertion power ratio and the magnitude squared of S21, they are very intimately related to each other. In fact, if we multiply IPR by S21 squared, if we multiply the two, what do we get? We get 4 R1 R2 divided by R1 plus R2 whole squared. Is that okay? This and this cancel, and by multiplication R2 and R2 cancel, so 4 R1 R2 divided by this. Alright, and the interesting result is that the product is a constant. Product only depends on the terminating resistances at any frequency, and you also notice that if it is an equally terminated network, that is, if R1 is equal to R2, then this product IPR and S21 squared would be equal to 1. So, one is the reciprocal of the other. Alright. This relationship was utilized by a gentleman named Darlington, who died at the age of 99 a few years ago. Sidney Darlington utilized this result to synthesize networks, and this is our first glimpse into network synthesis. He synthesized networks from the given S21 j omega squared, that is, from the given forward transmission scattering parameter. He was able to synthesize networks which have equal terminate. To be specific, well, he did it for the most general case, but for our purpose at this moment, let us say that we are considering equally terminated networks. That is, our problem is to synthesize a network N, and let us make it lossless. What does that mean? It only contains pure inductors and pure capacitors. R1 equal to R2, so equal terminations. If this is R, this is also R, and this is Vg1 and this is V2. Suppose this is specified S21 j omega squared. Now, usually this is not what will be specified. What will be specified will be the voltage ratio V2 by Vg1, the transfer function. But if you know what is V2 by Vg1, then you also know S21, isn't that right? Because S21 is simply twice V2 by Vg1. So, S21 j omega squared would be 4. Suppose this is given, H of S equal to V2 by Vg1. If this is given, then what is S21 j omega squared, magnitude squared? This is simply, yes, not twice, 4 times H of j omega magnitude square. So, if the if this is given S21 j omega squared, or the voltage transfer function is given, or something else, if the insertion power ratio is given, then you know insertion power ratio and S21 j omega squared, they are reciprocals of each other, and therefore in any of these circumstances you can find out what S21 j omega magnitude squared is, and from this Sidney Darlington was able to synthesize the network, and the steps are like this. Oh, let me also mention that sometimes the insertion power ratio, most of the times the insertion power ratio is given in decibels, and therefore insertion power ratio in decibels, IPR in dB would be equal to what? 10 log 10 the IPR, that is P2 by P20 by P2. Okay, insertion power ratio is P20, that is the power without the network divided by the power with the network. So, if this is given in decibel, then you have to find out the IPR by taking the ordinary ratio, that is decibel divided by 10 and then e to the power that. Okay, and this is sometimes in the literature is called the insertion power loss. Insertion power loss. Why is it a loss? If you recall, IPR is equal to P20 by P2. Why is it a loss? Because usually P20 is less than P2. Can P20 be greater than P2? The question. Yes, it can be. Pardon me? No, even otherwise. I can make a mess. I can make a mess of the network. I can design it such that it's not. But that's not the purpose. The purpose of an insertion network. Insertion network costs money. It contains inductors and capacitors. Why should one use it? One uses it only to increase the power transfer. That is, usually P2 is greater than P20, and therefore this quantity is less than 1. Taking log, it will give a negative sign, minus, and that's why it is a loss. Is that okay? Is that clear? That's why it is a loss. Alright. So insertion power loss is defined as 10 log 10 IPR, insertion power ratio.
So for a system R1 is for which R1 is equal to R2, we will have S21 mod of S21 j omega whole square always greater than 1 in this case if IPR is less than 1.
No, say it again.
Say if IPR is less than 1 as you were saying just now, then from that equation S21 mod S21 whole square into IPR is equal to 1.
Correct.
So S21 will always be greater than 1.
Has anybody an answer to this question? You see, the network itself does not absorb any power, and therefore whatever power is fed must go to the load. The rest of it shall come back. So it is a maximum condition that S21 magnitude squared can be equal to 1. Alright? It's a maximum, otherwise it will always be less than 1. Okay? Alright. Let me take an example of synthesis, then you will understand this problem. Yes, your question is still not fully answered, but I think you would get the answer as I go ahead. Well, the question is S21 j omega squared is given. Given. Let me set the problem. This is given as a function of omega, as a function of frequency. Okay? And it is given that R1 equal to R2. The terminations are equal. The problem is to design the lossless network N. Find N. This is the synthesis problem. Alright? This relates the response to the excitation. It is proportional to twice V2 by Vg1 magnitude squared. This is given and the terminating conditions are given. You are required to find the network N. So the first thing that you do is you recall that S11 j omega squared and N we want it to be lossless. We don't want N to absorb power, because then the power available to the load shall be reduced by the power absorbed by the network. So we want a lossless network. And no, we don't want. Without finding the transfer function. We want to realize the network. We want to find out what network shall realize this S21 j omega magnitude square. Okay. So we recall that for a lossless network, S11 magnitude squared plus S21 magnitude squared is equal to 1. Therefore, this is equal to 1 minus S21 j omega magnitude squared. So if this is given, then you can find out the input reflection coefficient magnitude squared. Alright? And at this point comes a big leap forward, and that is the following. You see, S11 j omega squared can be found out, and this is a parameter. If you take the total complex plane, it is the values are given on one of the axes, that is the imaginary axis. Okay? Can I find out the value of the parameter S11 at any other value of S. It turns out this is a partial specification on the j omega axis. The question is, can you find out the value at some other frequency which is not on the j omega axis? Can you do that? It turns out from the theory of complex variables that this can be done provided the function S11s is, what is the word for it? Have you done a course on complex variables? Yes. Analytic. What is an analytic function?
It has all differential of all orders at every point
Except
singularities.
except at a finite number of singularities. Okay. So, without going into details, our network functions are very well behaved. Otherwise, engineers would not have liked them. Engineers would not use them if they are not well behaved. Okay. It turns out that S11s is indeed well behaved. That is, it is analytic, and therefore, for an analytic function, one can go from partial specification to complete specification, which means that I write this expression as S11 j omega, S11 star j omega, all right, the left hand side. This is, there is nothing hidden in this. This is obvious, isn't it? Magnitude squared is equal to the quantity multiplied by its complex conjugate. And then what I do is I take a big leap forward, that is, from the imaginary axis I jump to any other point in the S axis, in the S plane, which means that I replace j omega by S. But before that, if it is an analytic function, what is the relation between this and this? It is only j omega is replaced by minus j omega, that is all. Okay. And therefore, what I get from this is S11 j omega multiplied by S11 minus j omega. And therefore, my final relationship is that S11 j omega, S11 minus j omega is equal to 1 minus mod S21 j omega magnitude squared. And from this relation, I know this now, from this relation I put j omega equal to S. This procedure, as I have said again and again, is valid only if the function S11 of small s is an analytic function, and this procedure is therefore given the name of analytic continuation, and the meaning of the two words should be obvious. It can be done only if the function is analytic, and it is a continuation of the value of the function from the j omega axis to any other point in the S plane, analytic continuation, and therefore you can find out S11s multiplied by S11 of minus S. And the next step is to find out what is S11 of S. Okay, what is given is S11 of S multiplied by S11 of minus S. How do you find out S11 of S? Now, if you recall the definition of S11 of S, what is the definition? Input impedance minus R1 divided by input impedance plus R1. Okay. Now, let me go slow. What is the property of input impedance Z1? Where should its poles be? Poles of an input impedance. It's a passive lossless network terminated in a resistance. Can it have poles in the right half plane? No, its poles must be on the left half plane. Now, Z1 plus R1, if you add a constant, obviously poles will change, but can they go to the right half plane? Yes or no? What is Z1 plus R1? It is a series combination of a resistance R1 and an impedance Z1. It is still an impedance, and therefore
Adding won't change the poles.
Adding would change the poles. Yes, of course. Of course it would change the poles. Suppose I have a function like this, s square plus omega naught squared. You add a resistance A. Adding won't change the poles. You are quite right. Do you see that his claim is correct? If you add a resistance, the poles would not change, the zeros would change. Okay. Therefore, the poles of Z1 plus R1 are the same as the poles of Z1, but its zeros will change. Zeros of Z1 plus R1 shall change. Where can the zeros be? Can they be in the right half plane? This we have done again and again. You see, for an impedance, there can be neither zeros nor poles in the right half plane. Poles and zeros must be in the left half plane. Why? Because the reciprocal of an impedance is admittance, and admittance poles must also be in the left half plane. Okay? Things will become a bit more clear when we take an example, but stay with me. The problem here was to identify what is S11 of S. Obviously, S11 of S shall have poles which are in the left half plane, and S11 of minus S then shall have poles which are in the right half plane. Isn't that right? Therefore, from this decomposition you shall choose that part which has poles in the left half plane, and once you do that, once you are able to identify S11 of S, since this is equal to Z1 minus R1 divided by Z1 plus R1, you then find out Z1. This will be equal to R1 multiplied by 1 plus S11 of S divided by 1 minus S11 of S. This is the compendendo and dividendo. Okay? And the final task is to synthesize Z1. Alright, this is the total procedure, but let me go through the steps once again before I take up an example. The steps are, let me go back. Steps are that given S21 j omega squared or any other version, for example the IPR or the insertion loss or the voltage transfer function, anything that is given, you first find out this. Subtract this from 1 to get the magnitude squared of the input reflection coefficient, and then you make an analytic continuation. That is, you write this as S11 j omega, S11 minus j omega, and replace j omega by S. Okay? After you do that, you get a product of terms which can be identified as S11S and S11 of minus S. At this point, we recall the property of S11S, or the definition, and the definition says that its poles must be in the left half plane. If one part has poles in the left half plane, S11 minus S must have poles in the right half plane. So you take that part which has poles in the left half plane, and from there you construct the input impedance Z1, and then you synthesize Z1. Let us take an example. Suppose S21, follow this example carefully. Suppose S21 j omega squared is 1 by 1 plus omega to the 6. This is what is given as a function of omega. What kind of a filter is this? What kind of a filter is this? Obviously a low pass filter. Isn't that right? It is a low pass filter. At omega equal to 0, the value is 1, and as omega increases, it continuously decreases. What is the frequency at which the value is half? At omega equal to 1. All right. as you will know later, this is called a Butterworth filter, a Butterworth low pass filter. Butterworth low pass filter of order 3. The power of omega in the magnitude squared is 6. The order of S in H of S, the transfer function shall be 3. Therefore, it is a Butterworth low pass filter of order 3. And the first thing we do is S11 j omega magnitude squared. We subtract this from unity, so we get omega to the 6 divided by 1 plus omega to the 6. Alright. Then we argue that S11 of S multiplied by S11 of minus S shall be equal to the right hand side with j omega replaced by S. J omega replaced by S, that is omega replaced by S by J. If omega is replaced by S by J, can you tell me what the denominator shall be? Numerator minus S to the 6 and the denominator 1 minus S to the 6. Okay. Now what you have to do is to decompose this into S11S and S11 minus S. That is, in the denominator you have to identify those zeros which are in the left half plane. Now it is not too bad. Our situation is S11S, S11 minus S is equal to minus S to the 6. Then 1 minus S to the 6 you can write as 1 minus S cubed multiplied by 1 plus S cubed. And this you can write as, let us find out the zeros, minus S6, 1 minus S, 1 plus S squared, then 1 plus S, 1 minus S plus S squared. Agreed? I have factorized 1 minus S cubed and 1 plus S cubed. Now, which of these factors will have left half plane zeros? Obviously, this factor has a right half plane 0. 1 minus S, the 0 is at S equal to 1. This has a left half plane 0 at S equal to minus 1 and this. Agreed? Whole? Okay. I am talking of zeros of the denominator. Alright. In the denominator, you look at those factors which create a left half plane pole of S11. Alright. And therefore, for S11S, our choice should be 1 plus S multiplied by 1 plus S squared. Is that clear? The other factor 1 minus S and 1 minus S plus S squared obviously should go to S11 of minus S. Alright. The next question is, what do we take for the numerator? Should we take plus S cubed or minus S cubed? Why not minus? Minus S cubed, the zeros are at the origin. We can take either. Excellent. We can take plus or minus. Accordingly, we shall get two networks. Okay. Once we have found out S11S, let us say this is plus S cubed divided by, let's simplify this. It becomes S cubed plus 2S squared plus twice S plus 1. Then you find out Z1 as equal to R1. Let us take R1 as 1 ohm specifically. Let us take R1 as 1 ohm. Then this would be 1 minus S11 divided by, no, it is the other way around. It is 1 minus S1 plus S11 divided by 1 minus S11. Okay. So this is equal to twice S cubed plus twice S squared plus twice S plus 1, and in the denominator we shall have simply twice S squared plus twice S plus 1. This is my input impedance. And the last problem, last task in the process is to synthesize this impedance Z1. Okay? And it is a beauty of Darlington synthesis that the constraint of a termination of 1 ohm, the constraint that Z1 shall be a lossless network terminated in a resistance which is equal to the resistance at port 1, that is 1 ohm, has already been taken care of. And how to do this I shall demonstrate next time. Okay?